Tonight, we're going to talk about gravity, a force so familiar that most of the time, we do not notice it at all. It is there when a leaf drifts down from a tree. It is there when a raindrop falls from a cloud. It is there when your body rests gently against a bed, a chair, or the ground beneath you. It is there in the quiet pull that keeps the moon near the earth. And it is there in an enormous, silent dance of planets, stars, galaxies, and black holes. Gravity is one of the simplest things to feel and one of the deepest things to understand. You do not need to memorize any formulas tonight. You do not need to solve any problems. You do not need to hold every detail in your mind. Just listen slowly. Let each idea arrive, stay for a moment, and then drift away. If you understand something, that is lovely. If you miss something, that is also perfectly fine. The universe will still be here. Gravity will still be here, quietly holding everything together. So, take a slow breath. Let your shoulders soften. And let's begin with something very small. A leaf, a simple leaf, loosening from the branch of a tree. For a moment, it hangs in the air. Then it turns. It tilts. It begins to fall. Not in a straight line. Perhaps the air catches it. It rocks gently from side to side. It spins once and again. And finally, after its slow little journey, it reaches the ground. This small motion is easy to overlook, but inside it is one of the great stories of physics. The story of why things fall. The story of why planets orbit. The story of why stars form. The story of how space and time can bend. The story of gravity. Chapter 1. The quiet fact that things fall. Let's begin with the most ordinary observation. Things fall downward. A stone released from your hand falls to the ground. A cup slips from a table and drops to the floor. Rain falls from the sky. Dust slowly settles. Snowflakes drift downward in winter air. A waterfall pours from a cliff to the rocks below. We grow up with this fact so completely that it feels almost too obvious to question. Of course things fall. Of course down is down. Of course the ground is where things end up. But physics often begins by looking again at something obvious and asking very gently why. Why does the stone fall? Why does it not float upward? Why does rain come down from clouds instead of drifting away forever? Why does your body have weight? And why does the moon, which is also being pulled by the earth, not simply fall down onto us? These questions may sound different, but they are connected by the same idea: gravity. At the most basic level, gravity is an attraction between things that have mass. Mass is a measure of how much matter something has. A grain of sand has a tiny amount of mass. Your body has more. The earth has an enormous amount. The sun has much, much more. And every bit of mass attracts every other bit of mass. This means that you are attracting the earth, and the earth is attracting you. But because the earth is so massive, its pull on you is what you feel. You feel it as weight. You feel it as the gentle pressure of your body against the surface beneath you. You feel it every time you lift something heavy. You feel it every time you climb stairs. You feel it when you jump, rise for a moment, and then return to the ground. Gravity is always present, but it is usually quiet. It does not announce itself. It does not flash or spark. It simply pulls. Constantly, patiently, every second of every day. And because it is always there, we often forget how strange it really is. Imagine, for a moment, that you had never seen anything fall. Imagine a world where objects simply stayed wherever you place them in the air. A cup could hover beside a table. A book could remain suspended above the floor. A drop of water could hang in front of your face, perfectly still. Then imagine seeing something fall for the first time. It would seem mysterious, almost magical. Something invisible would be pulling it downward. Something you could not see, but could clearly observe through its effect. That is one of the first lessons of physics. Many of the most important things in nature are invisible. We cannot see gravity itself. We see what gravity does. We see falling leaves. We see rivers flowing downhill. We see ocean tides rising and falling. We see planets tracing quiet paths around the sun. We see galaxies held together over immense distances. Gravity is known by its consequences, like the wind moving through trees. You do not see the wind itself. You see the leaves move. You hear the branches shift. You feel the air on your skin. In a similar way, we do not see gravity directly. We see the universe responding to it. Chapter 2, Weight Balance and the Feeling of Being Held. When you are standing still, it may feel like nothing is happening. You are not falling. You are not rising. You are simply there. But physics tells us that even stillness can be full of forces. The earth is pulling you downward. At the same time, the floor is pushing upward on you. This upward push is called a normal force. It is a support force from a surface. When these two forces balance, you remain still. Gravity pulls down. The floor pushes up. And because the two effects balance each other, your body stays in place. This is a gentle but important idea. Stillness does not always mean the absence of forces. Sometimes stillness means balance. A book resting on a table is not force-free. Gravity pulls the book down. The table pushes the book up. The book remains still because the forces are balanced. A person sitting in a chair is not floating free from physics. Gravity pulls the person downward. The chair supports them upward. The body rests in equilibrium. Equilibrium is a peaceful word. It means balance. It means that opposing influences have settled into a kind of agreement. In daily life, we experience equilibrium constantly. A lamp on a desk, a cup on a shelf, a mountain standing beneath the sky, a bridge holding steady across a river. Everything is being pulled by gravity. Everything is being supported, compressed, stretched, or balanced in response. Your sense of weight comes from this relationship. If you stand on a scale, the scale is not directly measuring gravity in a simple way. It is measuring how strongly it must push up against you to support you against gravity. That upward support is what becomes your weight reading. This is why astronauts in orbit appear weightless, even though gravity is still acting on them. They are not beyond Earth's gravity. They are falling around the Earth. And because everything around them is falling together, they do not feel the usual support force pushing up against them. Without that support force, they feel weightless. This is a subtle idea, so let's take it slowly. Weight is not just gravity. Weight is what you feel when something supports you against gravity. If you are standing on the ground supports you. If you are sitting in a chair, the chair supports you. If you are lying in bed, the bed supports you. The gentle pressure you feel is a pressure of support. Gravity pulls you down. The world holds you up. This is one of the quiet, physical truths of resting. To rest is not to escape gravity. To rest is to be held against it. Chapter 3, Galileo and the Falling Objects. For a long time, people thought heavier objects naturally fell faster than lighter ones. It seems reasonable at first. A stone falls faster than a feather. A heavy object often feels more eager to drop, but appearances can be misleading. The feather does not fall slowly because gravity barely pulls on it. It falls slowly because air gets in the way. Air resistance matters. A feather has a wide, delicate shape. As it falls, it must push through air. The air pushes back. A stone, being compact and dense, cuts to the air more easily. So in ordinary life, the stone reaches the ground first. But if you remove the air, something beautiful happens. The feather and the stone fall together. They accelerate downward at the same rate. This idea is often associated with Galileo. Whether or not every famous story about him is exactly true, the idea he helped bring into focus was revolutionary. Falling is not simply about heaviness. In the absence of air resistance, objects near Earth's surface fall with the same acceleration. This acceleration is usually called g. Near the surface of the Earth, it is about 9.8 meters per second squared. But you do not need to remember the number. The feeling is more important for tonight. Gravity does not just make things move downward. It makes them speed up as they fall. A falling object starts from rest. Then it moves faster. Then faster still. Every second, its downward speed increases. This is acceleration. Acceleration means a change in velocity. Velocity means speed with direction. So when a stone falls, gravity is not merely placing it somewhere lower. Gravity is continuously changing its motion. It is adding downward speed moment by moment. In everyday life, We rarely notice this precisely. A dropped object reaches the ground quickly. The moment is over. But if you could watch in slow motion, you would see the motion grow. First gentle, then faster, then faster. A small, steady increase. This steady increase is one of the simplest signatures of gravity near Earth, and it connects falling stones to falling rain, falling snow, falling apples, and even to the curves followed by projectiles. Throw a ball gently into the air. It rises, it slows. For a tiny moment at the top, it seems almost still, then it falls. As it comes down, it speeds up again. Gravity has been pulling the whole time. On the way up, gravity slows the ball. At the top, gravity is still pulling. On the way down, gravity speeds it up. One force. Different parts of the motion. A quiet rule underneath a familiar arc. Chapter 4, Newton's Great Connection. One of the most beautiful moments in the history of science came from connecting two things that seemed separate, a falling apple and the moon in the sky. The apple falls down to the earth. The moon stays above us, moving around the earth month after month. At first, these seem like different kinds of events. One is earthly, one is celestial. One happens in a garden, one happens in the heavens. But Isaac Newton saw that perhaps they belong to the same story. What if the force that pulls an apple downward is also the force that holds a moon in its orbit? What if Earth's gravity does not stop at the tops of trees or mountains or clouds? What if it extends outward into space, getting weaker with distance, but never simply vanishing? This was a profound idea. It meant that the same physical laws apply on Earth and in the sky. The universe is not divided into a lower world of ordinary matter and an upper world of perfect celestial motion. It is one universe, with one set of laws. Newton described gravity as a force of attraction between masses. The greater the masses, the stronger the attraction. The farther apart they are, the weaker the attraction. Again, you do not need to hold the formula in your mind, only the shape of the idea. More mass means more gravitational pull. More distance means less gravitational pull. The Earth pulls on the moon pulls on the Earth, the sun pulls on the Earth pulls on the sun. Every body pulls on every other body. But the effects we notice most are usually caused by very massive objects. The Earth, the moon, the sun, the planets. Gravity becomes especially important when mass is large and distances are astronomical. This is why gravity is the great architect of the cosmos. On small scales, other forces can dominate. Electromagnetic forces hold atoms and molecules together. Chemical bonds shape the materials around us. But on the scale of planets, stars, and galaxies, gravity becomes a main sculptor. It gathers gas into stars. It holds planets in orbit. It shapes galaxies. It bends the paths of light. And under extreme conditions, it forms black holes. Newton's insight was not just that gravity exists. It was that gravity links the ordinary and the cosmic. The falling apple and the orbiting moon are part of the same law. The ground beneath your feet and the motion of distant planets are connected. This is one of the quiet wonders of physics. A rule discovered in everyday experience can reach all the way to the stars. Chapter 5. The moon is falling around the Earth. Now, let us return to the moon. The moon is often described as orbiting the Earth. That is true, but there's another way to say it that feels more surprising. The moon is falling. It is falling toward the Earth, but it is also moving sideways. And because it is moving sideways fast enough, it keeps missing the Earth. This is what an orbit is, a fall that never lands. Let us imagine it step by step. Suppose you stand on a tall mountain and throw a stone forward. The stone moves forward, but gravity pulls it downward. It follows a curved path and hits the ground. Now imagine throwing harder. It travels farther before hitting the ground. Harder still, and it travels farther. Now imagine there were no air resistance, and you could throw it incredibly fast. So fast that as it falls, the earth curves away beneath it. The stone falls, but the ground keeps dropping away at the same rate. The stone never reaches the surface. It goes around the earth. It is an orbit. This is not something we can do by hand, of course, but it is the basic idea behind satellites. A satellite is not floating, because gravity has disappeared. It is continuously falling around the Earth. The moon, too, is always being pulled inward by Earth's gravity. If the moon had no sideways motion, it would fall directly toward Earth. If there were no gravity, the moon would move off in a straight line. But because it has sideways motion and gravity pulls it inward, it follows a curved path, an orbit. This balance between forward motion and inward pull is one of the most elegant ideas in classical physics. It explains the moon around the Earth. It explains the Earth around the sun. It explains satellites around planets. It explains comets sweeping around the sun in long elliptical paths. An orbit is not motion without gravity. It is motion shaped by gravity. This idea can feel calming when you sit with it. The moon is not held by a string. It is not resting on anything. It is not placed in the sky like a lamp. It is moving, falling, missing, returning, again and again. A quiet, repeating motion, a gravitational rhythm. Every month, the moon continues its long fall around our planet. And every night, whether we see it or not, it remains part of Earth's gravitational story. Chapter 6, Gravity and the Ocean Tides. Gravity is not only found in falling objects and orbiting moons. It also moves the oceans. The tides are one of the most graceful, everyday signs of gravity acting across distance. If you have ever watched the sea over many hours, you may have noticed that the waterline changes. At one time, the water reaches farther up the shore. Later, it retreats. Rocks appear. Sandbars emerge. Boats rise and fall. This slow breathing of the ocean is caused mostly by the gravitational pull of the moon, with help from the sun. The moon pulls on the Earth. It pulls on the oceans. The water on the side of Earth facing the moon is pulled slightly more strongly than the center of the Earth. This creates a bulge of water. On the far side of the Earth, another bulge forms because the Earth itself is pulled slightly more strongly than the water on that far side. As the Earth rotates, different coastlines pass through these bulges. The sea rises and falls. High tide, low tide, high tide again. It is a slow rhythm written by gravity. The moon does not need to touch the ocean to move it. It pulls from far away, across empty space, across nearly 400,000 kilometers, and the water responds. This is another reminder that gravity is not blocked by distance in the way ordinary contact forces are. You push a door by touching it. You lift a cup by holding it. But gravity reaches. It acts across space. The moon reaches toward the sea. The sun reaches toward the planets. The Earth reaches toward your body. And every object, however small, reaches in its own tiny way toward every other. The tides also remind us that gravity can stretch. The side of Earth nearest, the moon feels a slightly stronger pull than the side farther away. This difference in gravitational pull is called a tidal effect. Tidal effects are small on Earth, but they can become enormous near very massive objects, such as black holes. Their gravity can vary so strongly from one point to another that it can stretch matter dramatically. But in the familiar case of the ocean, tidal forces are gentle. They lift water. They lower water. They create daily rhythms along coastlines. If falling leaves show gravity in a moment, tides show gravity in a cycle, a slow, patient motion. The moon calling softly to the sea. Chapter 7, Gravity Builds Worlds. Gravity does not only make things fall after worlds already exist. Gravity helps build the worlds themselves. Long before a star shines, there can be a vast cloud of gas and dust, cold, thin, spread across space. At first, such a cloud may seem almost empty, but it has mass. And because it has mass, it is gravity. Tiny regions that are slightly denser than others pull in nearby material. As they gather more matter, their gravity grows stronger. As their gravity grows stronger, they gather even more matter. A slow collapse begins. The cloud contracts. It becomes denser. It warms. Eventually, in the center of a collapsing cloud, pressure and temperature can rise so much that a star is born. A star is not simply a ball of fire. It is a balance. Gravity pulls inward. The heat and radiation from nuclear fusion push outward. For much of a star's life, these two tendencies hold each other in balance. Inward gravity. Outward pressure. The star shines because it is held in this delicate equilibrium. Here again, stillness or stability does not mean nothing is happening. A star can look steady in the night sky, but inside it, unimaginable processes are taking place. Gravity compresses. Fusion releases energy. Light streams outward. Matter holds together. A star is a gravitational object, a furnace, and a balance all at once. Around young stars, leftover gas and dust can form disks. Within those disks, small grains collide and stick. They form pebbles, then rocks, then larger bodies. Gravity helps them gather more material. Over time, planets can form. So the ground beneath your feet, the mountains, the oceans, and the air above you all have a long gravitational history. The Earth formed because gravity gathered matter together. The sun formed because gravity collapsed a cloud. The solar system exists because gravity organized motion. Gravity does not only pull things downward. It gathers, it shapes, it builds. It turns diffuse clouds into stars. It turns scattered debris into planets. It turns collections of stars into galaxies. On cosmic scales, gravity is a kind of quiet builder. It works slowly, often over millions or billions of years. It does not rush. But given enough time, gravity can transform emptiness into structure, clouds into stars, dust into planets, chaos into orbits. Chapter 8, Escape Velocity and Leaving Earth. If gravity pulls everything toward Earth, how can anything leave? How can a rocket rise into space? How can a spacecraft travel to the moon? The answer is not that gravity suddenly stops. The answer is motion. To leave Earth, an object must move fast enough to climb out of Earth's gravitational pull without falling back. This required speed is called escape velocity. Near Earth's surface, escape velocity is about 11.2 kilometers per second. Again, the number is not important for rest tonight. The idea is enough. If you throw a ball upward gently, it rises for a moment and falls back. Throw it faster and it rises higher. Faster still, and it rises higher still. If there were no air resistance, and if you could throw it with enough speed, it would never return. It would escape Earth's gravitational hold. Rockets do not leave Earth because they defeat gravity once and for all. They leave by continuously pushing, accelerating, and gaining enough energy to climb away. Even far from Earth, gravity remains. It simply becomes weaker with distance. This is why spacecraft trajectories are carefully planned. A spacecraft leaving Earth may be influenced by Earth, the Moon, the Sun, and other planets. Gravity becomes a landscape through which the spacecraft moves. Mission planners can even use gravity to help. A spacecraft can pass near a planet and gain speed or change direction through a gravitational assist. This is sometimes called a slingshot maneuver. The spacecraft falls toward a planet, swings around it, and leaves along a new path. Gravity, which might seem like an obstacle, becomes a guide. This is a lovely idea. The same force that keeps us grounded can also help send explorers outward. The same gravity that pulls a stone down can shape the journey of a spacecraft across the solar system. Physics is often like this. A force is not simply good or bad. It is a rule, a pattern, a way nature behaves. When we understand the pattern, we can move with it. Rockets rise through gravity. Satellites fall around Earth. Spacecraft glide through the gravitational fields of planets. Leaving Earth is not escaping physics. It is using physics very carefully. Chapter 9, Einstein's softer picture of gravity. Newton described gravity as a force between masses. This picture works beautifully for many things. It describes falling objects' orbits, tides, and the motion of planets with remarkable accuracy. But centuries later, Albert Einstein offered a deeper picture. In Einstein's theory of general relativity, gravity is not simply a force pulling across space. Gravity is connected to the shape of space and time themselves. This may sound strange, so let's approach it slowly. Imagine a smooth fabric stretched out flat. Now, place a heavy ball in the middle. The fabric curves downward around the ball. If you roll a smaller ball nearby, it may curve around the heavy ball, not because an invisible string pulls it, but because the surface it moves on is curved. This image is often used to introduce general relativity. It is not perfect. No analogy is perfect, but it gives a feeling for the idea. Mass and energy change the geometry around them. Objects then move according to that geometry. In Einstein's view, the Earth moves around the Sun because the Sun curves spacetime, and the Earth follows a natural path through that curved spacetime. The Moon follows a path through spacetime shaped by the Earth. Light, too, can follow curved paths when passing near massive objects. This is one of the remarkable predictions of general relativity. Gravity can bend light, not because light has ordinary mass like a stone, but because light travels through spacetime, and spacetime itself can be curved. This bending of light has been observed. When light from a distant star or galaxy passes near a massive object, its path can curve. Sometimes gravity can act like a lens, magnifying or distorting the image of distant objects. This is called gravitational lensing. A massive galaxy cluster can bend the light from galaxies behind it. Space becomes a lens. Gravity becomes visible through the paths of light. General relativity also changes how we think about time. Gravity affects time. Clocks closer to a massive object tick slightly more slowly than clocks farther away. Near Earth, the effect is tiny, but it is real. Near a black hole, it can become dramatic. Time and gravity are not separate in Einstein's picture. They are part of one fabric. Spacetime. This idea is deep, and it is okay if it feels strange. It should feel strange. It asks us to imagine that space is not merely an empty stage where things happen. Space and time are part of the physical universe. They can stretch. They can curve. They can respond to matter and energy. Gravity, in this view, is geometry becoming motion. A planet follows a curve. Light follows a curve. Time itself changes its pace. All because mass and energy shape space-time. Newton gave us gravity as a force. Einstein gave us gravity as curvature. Both pictures are useful. Newton's picture is often enough for everyday life and many engineering problems. Einstein's picture becomes important when gravity is very strong, speeds are very high, or measurements are extremely precise. Together, they give us a richer understanding. A falling leaf can be understood with Newton. A black hole needs Einstein, and both are part of the same long story of gravity. Chapter 10, Black Holes, where gravity becomes extreme. Now let us drift slowly toward one of the most mysterious objects in physics, a black hole. A black hole is a region where gravity is so strong that nothing, not even light, can escape once it passes a certain boundary. That boundary is called the event horizon. The event horizon is not a solid surface. You could not land on it like the ground. It is a point of no return, a boundary in space-time. Outside it, escape may still be possible. Inside it, every path leads inward. To understand how a black hole can form, we can return to stars. A massive star spends much of its life balancing gravity and pressure. Gravity pulls inward. Fusion in the core creates outward pressure. But eventually, a massive star can run out of usable fuel in its core. When outward pressure can no longer support the star, gravity wins. The core collapses. If the remaining mass is large enough, the collapse can continue until a black hole forms. Matter has become so compact that the escape velocity exceeds the speed of light. And since nothing can travel faster than light, nothing can escape within the event horizon. This may sound frightening, but we can hold the idea gently. A black hole is not a cosmic vacuum cleaner, sucking everything in from across the universe. If the sun were magically replaced by a black hole of the same mass, Earth would not suddenly be pulled in. It would continue orbiting the same way, because the mass would be the same. The danger of a black hole lies in getting very close. Near a black hole, gravity becomes intense. Tidal forces can become enormous. Time can slow dramatically relative to faraway observers. Light can curve into strange paths. Matter falling toward a black hole can heat up and glow brightly before crossing the event horizon. In this way, black holes can be dark and bright at the same time. The black hole itself emits no light from within the horizon, but the material around it can shine intensely. Black holes also teach us that gravity is not merely a weak background force. Under extreme conditions, gravity can dominate everything. It can trap light. It can reshape time. It can challenge our understanding of quantum physics and information. At the center of many galaxies, including our own Milky Way, there are supermassive black holes. These objects contain millions or billions of times the mass of the Sun. They sit in galactic centers, influencing the motion of stars and gas around them. And yet from far away, they are part of the quiet architecture of galaxies. Black holes remind us that gravity has depths. The same gravity that brings a leaf to the ground can, in another setting, curve space-time so strongly that light cannot return. The same principle across an enormous range of scales, from the gentle fall of rain to the edge of a black hole. Chapter 11, Gravity Waves Through Space-Time. Einstein's theory also predicted something very subtle and beautiful: gravitational waves. These are ripples in space-time itself. Imagine two massive objects orbiting each other, such as two black holes. As they move, they disturb space-time. Those disturbances can travel outward as waves, like ripples spreading across the surface of a pond. But instead of ripples in water, these are ripples in the geometry of space and time. For a long time, gravitational waves were only a prediction. They were expected to be extraordinarily difficult to detect because by the time they reach Earth, their effects are incredibly tiny. They stretch and squeeze space by amounts far smaller than the width of an atom. And yet, in 2015, scientists directly detected gravitational waves for the first time. The waves came from two black holes merging far away in the universe. For a brief moment, the collision released an enormous amount of energy in the form of gravitational waves. By the time those waves reached Earth, they were faint whispers, but our instruments heard them. This was a new way of observing the universe. Before, astronomy mostly used light, visible light, radio waves, X-rays, infrared radiation, and other forms of electromagnetic radiation. But gravitational waves are different. They are not light. They are vibrations of space-time itself. They allow us to sense events that may be invisible or difficult to study with ordinary telescopes. Black hole mergers, neutron-star collisions, extreme gravitational dances. The detection of gravitational waves showed, in a very direct way, that space-time is not rigid. It can ripple. It can carry energy. It can transmit the memory of violent cosmic events across billions of light years. And by the time those waves reach us, they are almost unimaginably gentle. A faint stretching, a faint squeezing, a whisper from deep space. This is another side of gravity. Not just pulling, not just orbiting, not just bending, but waving. Space-time itself trembling softly after distant black holes collide. Chapter 12, Gravity, Time, and Everyday Precision. General relativity may sound like something only needed for black holes and galaxies, but gravity's effect on time matters even close to home. Consider GPS. The satellites that help determine positions on Earth carry extremely precise clocks. These clocks are moving quickly relative to us, and they are also higher in Earth's gravitational field. Both motion and gravity affect the rate at which time passes. If engineers ignore relativity, GPS will become inaccurate. Tiny differences in time would build up into large errors in position. So even when you use a phone to navigate, you are quietly depending on Einstein's understanding of gravity and time. This is a wonderful reminder. Deep physics is not always far away. Sometimes it is hidden inside ordinary technology, inside satellites, inside timing signals, inside the maps that guide people through cities. Gravity affects clocks. A clock closer to Earth's surface, deeper in Earth's gravitational field, ticks slightly differently from a clock farther away. The difference is tiny but measurable. This means time is not the same everywhere in a gravitational field. It is not a single universal river flowing identically for all observers. Time has local character. It depends on motion. It depends on gravity. It depends on where and how you are moving through space-time. This can feel unsettling at first, but it can also feel beautiful. The universe is more flexible than everyday intuition suggests. Space can curve. Time can stretch. Clocks can disagree, not because they're broken, but because reality itself allows different paths through time. Gravity is part of that story. Not only does it shape motion, it shapes duration. It shapes the rhythm of clocks. It shapes the relation between one moment and another. Even here near Earth, where gravity feels ordinary, the deeper truth is present. Every second passes inside a gravitational field. Every clock ticks in spacetime. Every moment is part of the geometry of the universe. Chapter 13, Why Gravity Feels Weak, Yet Shapes the Cosmos. There is something curious about gravity. In one sense, it seems powerful. It holds the moon near Earth. It holds Earth near the sun. It holds galaxies together. It forms stars, planets, and black holes. But in another sense, gravity is extremely weak compared with other fundamental forces. You can feel this in a simple way. Take a small magnet and hold it near a paperclip. The magnet can lift the paperclip upward against the gravitational pull of the entire Earth. A small magnet, using electromagnetic force, can overcome the gravity of a planet. That is remarkable. Gravity is weak between ordinary small objects. You and a nearby book attract each other gravitationally, but the attraction is far too tiny to notice. Two chairs attract each other. Two cups attract each other. Every object with mass attracts every other. But unless it leaves where the object has a very large mass, the effect is usually negligible. So, why does gravity dominate the universe at large scales? One reason is that gravity always attracts. Electric charges can be positive or negative. Opposite charges attract, like charges repel, and large collections of matter are often electrically neutral overall. But mass does not come in positive and negative forms that cancel gravity in the same ordinary way. Mass attracts mass. Energy gravitates too. So over large distances and enormous amounts of matter, gravity accumulates. It adds up. Stars, planets, galaxies, and clusters of galaxies are all shaped by this accumulated pull. Gravity may be weak in a small room, but given a planet, it becomes the weight of oceans and mountains. Given a star, it becomes a force holding a nuclear furnace together. Given a galaxy, it becomes the architecture of hundreds of billions of stars. This is one of the paradoxical beauties of gravity. It is gentle enough that you can lift your hand, but vast enough to organize the cosmos. Weak in the small, majestic in the large, quiet nearby, dominant across the stars. Chapter 14, Gravity and the Shape of the Universe. When we look at the universe on the largest scales, gravity is everywhere. Galaxies are not scattered completely at random. They gather into groups, clusters, and vast filaments. Between these filaments are enormous cosmic voids. The large-scale structure of the universe looks something like a web, a cosmic web. Gravity helped form this web. In the early universe, matter was not perfectly uniform. Some regions were slightly denser than others. Those denser regions had slightly stronger gravity. They pulled in more matter. As they gained more matter, their gravity grew stronger. Over billions of years, small differences grew into large structures. Galaxies formed, clusters formed, filaments formed. Gravity amplified the tiny unevenness of the early universe in the grand structure we see today. This is a theme we have already met. A slightly denser cloud can gather more gas and become a star. A slightly denser region in the early universe can gather matter and become part of a galaxy cluster. Gravity rewards density. Where there is a little more matter tends to gather. This does not happen instantly. Gravity is patient. It works over long times, over millions of years, over billions of years. The universe we see today is a result of gravity working slowly across cosmic time. There is another mysterious piece here. Most of the matter that helps shape galaxies and clusters appears to be dark matter. Dark matter does not emit light in the ways ordinary stars and gas do. We infer its presence from its gravitational effects. Galaxies rotate in ways that suggest more mass than we can see. Galaxy clusters bend light more than visible matter alone can explain. The cosmic web itself seems to have formed under the influence of dark matter. We do not yet know exactly what dark matter is, but we know it gravitates. Once again, gravity reveals the invisible. It shows us the presence of something we cannot directly see, like wind in trees, like an unseen hand shaping motion. Dark matter is not understood by its light. It is known by its pull. Chapter 15, The gentle mathematics of gravity. Although this video is meant to be gentle and restful, we can still touch the mathematics lightly. Mathematics is the language in which gravity becomes precise. In Newton's theory, the gravitational force between two objects depends on their masses and the distance between them. More mass means more force. More distance means less force. Specifically, the force decreases with the square of the distance. This is called an inverse square law. If the distance doubles, the gravitational force becomes 4 times weaker. If the distance triples, it becomes 9 times weaker. This pattern appears in other parts of physics too, such as the spreading of light from a source. Why the square? One way to feel the idea is to imagine influence spreading outward in all directions. As it spreads, it covers the surface of a sphere. The surface area of a sphere grows with the square of the radius. So the same influence is spread over a larger and larger area. It becomes weaker with distance according to that square. Again, you do not need to calculate anything. Just notice the shape of the idea. Gravity fades with distance, but does not abruptly end. The Earth's gravity is strongest near Earth. It weakens as you move away, but it continues outward. The sun's gravity reaches across the solar system. The gravity of galaxies reaches across intergalactic space. Mathematics lets us describe these changes with clarity. It lets us predict where planets will be. It lets us send spacecraft to other worlds. It lets us measure the masses of stars. It lets us understand the bending of light and the timing of clocks. In physics, mathematics is not separate from beauty. A simple equation can hold a vast pattern. A small relationship between mass and distance can describe both a falling stone and the orbit of a planet. This is one reason gravity has fascinated scientists for centuries. It is both intimate and cosmic, simple enough to feel, deep enough to reshape our idea of reality. Chapter 16, Gravity in the Human Body. Gravity is not only astronomical, it is biological. Your body has grown and developed under gravity. Your bones support weight. Your muscles work against gravity. Your heart pumps blood in a body shaped by up and down. Your sense of balance depends partly on gravity. Inside your inner ear are tiny structures that help detect orientation and motion. They allow your brain to understand which way is up, how your head is tilted, and how your body is moving. Gravity is part of your sense of place. When astronauts spend long periods of microgravity, their bodies change. Bones can lose density. Muscles can weaken. Fluids shift. The body adapts to a new physical environment. This reminds us that gravity is not just something outside us. It is part of the conditions in which life on Earth evolved. Plants grow in response to gravity. Roots tend to grow downward. Stems tend to grow upward. This response is called gravitropism. Even a seed in dark soil can sense the direction of gravity. It sends roots toward the pole and shoots away from it. Life has learned gravity. Not consciously, of course, but structurally, biologically, over long evolutionary time. Gravity is written into posture, movement, growth, and rest. When you lie down at night, gravity changes how your body feels. The weight of your limbs is supported by the bed. Muscles that held you upright can soften. The body no longer has to balance in the same way. Rest is, in part, a new relationship with gravity. Instead of standing against it, you let the surface beneath you hold you. This is a gentle thought for sleep. You are not floating alone. You are supported. Gravity pulls. The world responds. And in that balance, your body can rest. Chapter 17, Gravity and the Sense of Down. Down feels obvious on Earth, but down is not the same everywhere. On a spherical planet, down means toward the center of the Earth. Someone standing on the other side of the planet is not upside down in any absolute sense. Their down is also toward Earth center. This can be a strange idea when first encountered, but it shows that down is local. Down is defined by gravity. Wherever you stand on Earth, gravity points roughly toward the center. That direction becomes down. Up is away from the center. On the moon, down means toward the moon center. On Mars, down means toward Mars' center. Near a small asteroid, gravity may be weak and irregular, and down may be less familiar. In deep space, far from large bodies, there may be no strong sense of down at all. Astronauts in orbit experience this. Inside a spacecraft, there is no natural floor in the same way there is on Earth. Objects can float. People can turn in any direction. Up and down become choices of orientation rather than absolute facts. This reminds us that some things we experience as universal are actually local features of our environment. Down is not a cosmic direction. It is the direction gravity pulls you. On Earth, that pull is steady and familiar, so down feels absolute. But physics gently reveals that our everyday intuition is shaped by our planetary home. We are Earth creatures. We think with Earth habits. Gravity gives us those habits. It gives us floors and ceilings, falling and rising, weight and balance, above and below. Our language is full of gravity. We fall asleep. We feel down. We rise in the morning. We lift our spirits. Gravity is so woven into experience that it becomes metaphor, not only a force in physics, but a structure in thought. Chapter 18, a slow walk to the scale of gravity. Let us now take a slow walk through scale. Begin with a grain of dust resting on a table. It has mass. It has gravity. It attracts the Earth, and the Earth attracts it. But the dust's own gravitational pull is unimaginably tiny. Now imagine a stone. More mass, more gravity. Still too small to notice as a source of gravity in ordinary life. Now a mountain. A mountain has enough mass that sensitive instruments can detect its gravitational effect. The mountain pulls slightly on nearby objects, very slightly. Now the Earth, large enough to hold an atmosphere, large enough to pull oceans around its surface, large enough to give weight to every object near it. Now the moon, smaller than Earth, but large enough to pull the oceans into tides. Now the sun, so massive that it holds the entire solar system in its gravitational influence. Planets, asteroids, comets, and distant icy bodies all move in paths shaped by the sun. Now a galaxy. Hundreds of billions of stars. Gas, dust, dark matter. All bound into a rotating structure by gravity. Now a galaxy cluster. Many galaxies held together. A vast gravitational system. Now the cosmic web. Filaments of matter stretching across the universe. Gravity acting over billions of years. At each scale, gravity appears differently. For dust, it is negligible. For a body, it is weight. For a moon, it is tides. For a planet, it is atmosphere and orbit. For a star, it is fusion and stability. For a galaxy, it is structure. For the universe, it is evolution. The same idea, wearing different forms. This is one of the pleasures of physics. A single principle can echo across scale. It can whisper in a falling leaf and roar in the collision of black holes. It can rest under your body and curve the path of light from distant galaxies. Gravity is not one story. It is many stories connected by one quiet thread. Chapter 19, Misconceptions about Gravity. Before we begin to settle toward the end, let us gently clear away a few common misunderstandings. The first is that there is no gravity in space. This is not true. Gravity exists in space. In fact, space is full of gravitational influence. The moon orbits because of gravity. Satellites orbit because of gravity. The International Space Station remains near Earth because Earth's gravity is still pulling on it. Astronauts appear weightless because they are in continuous free fall, not because gravity is gone. The second misunderstanding is that heavier objects always fall faster. In everyday air, this can appear true because of air resistance. But without air resistance, objects near Earth fall with the same acceleration regardless of mass. A hammer and a feather dropped on the moon fall together. The third misunderstanding is that orbits are places where gravity and motion somehow cancel out completely. In truth, gravity is what creates the orbit. Without gravity, an orbiting object would move in a straight line. With gravity, its path curves. An orbit is not freedom from gravity. It is a graceful partnership between motion and gravitational pull. The fourth misunderstanding is that black holes suck everything in endlessly. A black hole has gravity according to its mass. From far away, it behaves like any other object of the same mass. You must come very close for the extreme effects to dominate. The fifth misunderstanding is that gravity is completely understood. We understand a great deal. Newton's theory works beautifully in many situations. Einstein's theory works with astonishing precision in others. But gravity remains deeply mysterious when we try to combine it fully with quantum mechanics. A complete theory of quantum gravity is still one of the great open problems in physics. So gravity is both familiar and unfinished. We can calculate planetary motion. We can detect gravitational waves. We can correct satellite clocks. We can photograph the environment around black holes. And yet, at the deepest level, we are still learning what gravity is. This is not a failure of science. It is part of its beauty. Understanding grows. Questions become sharper. Old mysteries become new doorways. Gravity remains one of those doorways. Chapter 20, a gentle summary. Let us now gather the ideas softly. We began with a falling leaf, a small thing, a quiet motion. From there, we asked why things fall. We saw that gravity is an attraction between things with mass. The Earth pulls on you, and you pull on the Earth. Because the Earth is so massive, its pull shapes your everyday experience. It gives you weight. It defines down. It holds the atmosphere close. It draws rain from clouds and rivers toward the sea. We saw that stillness can mean balance. A book resting on a table is held between gravity pulling down and the table pushing up. Your body at rest is also in balance, supported against gravity. We saw that falling objects accelerate. In the absence of air resistance, different objects fall at the same rate near Earth's surface. We followed Newton's great connection between the falling apple and the orbiting moon. We saw that the moon is falling around the Earth. An orbit is a fall that never lands. We watched gravity move the oceans through tides. We saw gravity build stars, planets, galaxies in the cosmic web. We learned that rockets do not escape physics, but move with it, using energy and motion to leave Earth. We touched Einstein's deeper picture, where gravity is connected to the curvature of spacetime. We saw that gravity can bend light, slow time, and form black holes. We listened for gravitational waves, faint ripples from distant cosmic collisions. We noticed that gravity is weak in small things, but powerful across large scales because it adds up and always attracts. We saw that gravity shapes the body, the sense of down, the tides, the planets, the stars, and the structure of the universe. And we remember that even now, after centuries of study, gravity still holds mysteries. This is a good place to rest, not because the story is finished, but because it is enough for tonight. Gravity is easy to ignore because it is always with us. It is there in every step, every breath, every object resting on a shelf, every drop of rain finding its way downward, every wave pulled by the moon, every planet moving through the dark. It does not need to be loud. It does not need to glow. It does not need to call attention to itself. Gravity is patient. It works quietly. It holds worlds together. It gathers stars from clouds. It shapes galaxies from matter. It bends light from distant places. It slows time near massive bodies. It lets moons fall forever around planets. And here on Earth, it gives us the simple feeling of being grounded, of having a down, of being held. Tonight, as you rest, gravity is still here. The Earth is still turning. The moon is still moving around us. The planets are still following their quiet paths around the sun. The sun is still orbiting within the Milky Way. And the Milky Way is still moving through the larger structure of the universe. Nothing is truly still. Everything is moving, falling, orbiting, turning, drifting, held in invisible relationships across space and time. And yet, from here in this moment, it can all feel peaceful. A body at rest, a quiet room, a world beneath you, a sky above you, and gravity, gentle and constant, holding you softly to the earth. If your thoughts are becoming slower now, let them slow. If your body is becoming heavy, let it be heavy. That heaviness is not something to resist. It is the feeling of being supported. Gravity pulls you downward. The world holds you upward. And between those two quiet facts, rest becomes possible. So let the idea of gravity settle. Let the falling leaf reach the ground. Let the moon continue its endless fall around Earth. Let the oceans rise and fall. Let the stars shine in their long gravitational balance. Let distant black holes curve spacetime in silence. Let the universe continue its slow, immense dance. And for now, you do not need to follow all of it. You can simply rest. The laws of physics will keep going. The planets will keep moving. Gravity will keep holding the world. And the night can continue gently around you. Sleep well. If you enjoyed this calm journey through gravity, you can return anytime for more gentle physics stories about light, waves, time, stars, black holes, and the quiet laws of the universe. For now, thank you for listening, and good night.